Cobalt is a chemical element with symbol Co and atomic number 27. Like nickel, cobalt in the Earth's crust is found only in chemically combined form, save for small deposits found in alloys of natural meteoric iron. The free element, produced by reductive smelting, is a hard, lustrous, silver-gray metal. Cobalt-based blue pigments have been used since ancient times for jewelry and paints, and to impart a distinctive blue tint to glass, but the color was later thought by alchemists to be due to the known metal bismuth. Miners had long used the name kobold for some of the blue pigment-producing minerals. They were so named because they were poor in known metals, and gave poisonous arsenic-containing fumes upon smelting. In 1735, such ores were found to be reducible to a new metal, and this was ultimately named for the kobold. Today, some cobalt is produced specifically from various metallic lustered ores, for example cobaltite, but the main source of the element is as a byproduct of copper and nickel mining. The copper belt in the Democratic Republic of the Congo and Zambia yields most of the cobalt mined worldwide. Cobalt is primarily used as the metal, in the preparation of magnetic, wear-resistant and high-strength alloys. Its compounds cobalt silicate and cobalt, illuminate give a distinctive deep blue color to glass, smalt, ceramics, inks, paints and varnishes. Cobalt occurs naturally as only one stable isotope, cobalt-59. Cobalt-60 is a commercially important radioisotope, used as a radioactive tracer and for the production of high-intensity gamma rays. Cobalt is the active center of coenzymes called cobalamins, the most common example of which is vitamin B12. As such it is an essential trace dietary mineral for all animals. Cobalt in inorganic form is also an active nutrient for bacteria, algae and fungi. Characteristics: cobalt is a ferromagnetic metal with a specific gravity of 8.9. The Curie temperature is 1115 AA degrees Celsius and the magnetic moment is 1.6 A 1.7 Bohr-mountains per atom. Cobalt has a relative permeability 2/3 that of iron. Metallic cobalt occurs as two crystallographic structures, HCP and FCC. The ideal transition temperature between the HCP and FCC structures is 450 AA degrees Celsius, but in practice, the energy difference is so small that random intergrowth of the two is common. Cobalt is a weakly reducing metal that is protected from oxidation by a passivating oxide film. It is attacked by halogens and sulfur. Heating in oxygen produces Co3O4 which loses oxygen at 900 AA degrees Celsius to give them an oxide Co. The metal reacts with fluorine gas at 520 K to give CoF3. With chlorine, bromine and iodine, the corresponding binary halides are formed. It does not react with hydrogen gas or nitrogen gas even when heated, but it does react with boron, carbon, phosphorus, arsenic and sulfur. At ordinary temperatures, it reacts slowly with mineral acids, and very slowly with moist, but not with dry, air. Compounds. Common oxidation states of cobalt include +2 and +3, although compounds with oxidation states ranging from A3 to +4 are also known. A common oxidation state for simple compounds is +2. These salts form the pink-colored metal aqua complex, Co, H2O, 6, 2+ in water. Addition of chloride gives the intensely blue, CoCl, 4, 2A. Oxygen and chalcogen compounds, several oxides of cobalt are known. Green cobalt, oxide is rock salt structure. It is readily oxidized with water and oxygen to brown cobalt, hydroxide 3. At temperatures of 600 to 700 AA degrees Celsius, Co oxidizes to the blue cobalt, II, oxide, which has a spinel structure. Black cobalt, oxide is also known. Cobalt oxides are antiferromagnetic at low temperature, Co and Co3O4, which is analogous to magnetite, with a mixture of +2 and +3 oxidation states. The principal chalcogenides of cobalt include the black cobalt, sulfides, Cos, which adopts a pyrite-like structure, and cobalt, sulfide. Halides. 4 dilids of cobalt, unknown, cobalt, 2, fluoride, cobalt, 2, chloride, cobalt, 2, bromide, cobalt, 2, iodide. These halides exist in anhydrous and hydrated forms. Whereas the anhydrous dichloride is blue, the hydrate is red. The reduction potential for the reaction, Co3 plus EaCO2 plus, is plus 1.92 V, beyond that for chlorine to chloride, plus 1.36 V. As a consequence, cobalt, 3, and chloride would result in the cobalt, 3, being reduced to cobalt, 2. Because the reduction potential for fluorine to fluoride is so high, plus 2.87 V, cobalt, 3, fluoride is one of the few simple stable cobalt, 3, compounds. Cobalt, 3, fluoride, which is used in some fluorination reactions, reacts vigorously with water. Coordination compounds, as for all metals, molecular compounds and polyatomic ions of cobalt are classified as coordination complexes, that is molecules or ions that contain cobalt linked to several ligands. The principles of electronegativity and hardness or softness of a series of ligands can be used to explain the usual oxidation state of the cobalt. For example, company +3 complexes tend to have amine ligands. As phosphorus is softer than nitrogen, phosphine ligands tend to feature the softer Co2+ and Co+, an example being tris, triphenylphosphine, cobalt, I, chloride 3, 3-Co-Cl. The more electronegative oxide and fluoride can stabilize Co4+ and Co5+ derivatives, for example cesium hexafluorocobaltate and potassium percobaltate. Alfred Werner, a Nobel Prize-winning pioneer in coordination chemistry, worked with compounds of empirical formula, Co, NH3, 6, Cl3. One of the isomers determined was cobalt, 3, hexamine chloride. This coordination complex, a typical Werner-type complex, consists of a central cobalt atom coordinated by 6 amine ligands orthogonal to each other and 3 chloride counteranions. Using chelating ethylenediamine ligands in place of ammonia gives tris, ethylenediamine, cobalt, 3, chloride 3, Cl3, which was one of the first coordination complexes that was resolved into optical isomers. The complex exists as both either right or left-handed forms of a 3-bladed propeller. This complex was first isolated by Werner as yellow-gold needle-like crystals. Organometallic compounds. Cobaltocene is a structural analog to ferrocene, where cobalt substitutes for iron. Cobaltocene is sensitive to oxidation, much more than ferrocene. Cobalt carbonylate is a catalyst in carbonylation and hydrosylylation reactions. Vitamin B12 is an organometallic compound found in nature and is the only vitamin to contain a metal atom. Isotopes. 59Co is the only stable cobalt isotope and the only isotope to exist naturally on Earth. 22 radioisotopes have been characterized, with the most stable being 60Co with a half-life of 5.2714 years, 57Co with a half-life of 271.8 days, 56Co with a half-life of 77.27 days, and 58Co with a half-life of 70.86 days. All of the remaining radioactive isotopes have half-lives that are shorter than 18 hours, and the majority of these are shorter than 1 second. This element also has 4 metastates, all of which have half-lives shorter than 15 minutes. The isotopes of cobalt range in atomic weight from 50U to 73U. The primary decay mode for isotopes with atomic mass unit values less than that of the most abundant stable isotope, 59Co, is electron capture, and the primary mode of decay for those of greater than 59 atomic mass units is beta decay. The primary decay products before 59Co are element 26 isotopes and the primary products after are element 28 isotopes. History. Cobalt compounds have been used for centuries to impart a rich blue color to glass, glazes and ceramics. Cobalt has been detected in Egyptian sculpture and Persian jewelry from the 3rd millennium BC, in the ruins of Pompeii, and in China dating from the Tang dynasty and the Ming dynasty. Cobalt has been used to color glass since the Bronze Age. The excavation of the Uliburon shipwreck yielded an ingot of blue glass, which was cast during the 14th century BC. Blue glass items from Egypt are colored with copper, iron, or cobalt. The oldest cobalt-colored glass was from the time of the 18th dynasty in Egypt. The location where the cobalt compounds were obtained is unknown. The word cobalt is derived from the German kobold, from kobold meaning goblin, a superstitious term used for the ore of cobalt by miners. The first attempts at smelting these ores to produce metals such as copper or nickel failed, yielding simply powder oxide, instead. Also, because the primary ores of cobalt always contain arsenic, smelting the ore oxidized the arsenic content into the highly toxic and volatile arsenic oxide, which also decreased the reputation of the ore for the miners. Swedish chemist Georg Brandt is credited with discovering cobalt circa 1735, showing it to be a new previously unknown element different from bismuth and other traditional metals, and calling it a new semi-metal. He was able to show that compounds of cobalt metal were the source of the blue color in glass, which previously had been attributed to the bismuth found with cobalt. Cobalt became the first metal to be discovered since the prehistorical period, during which all the known metals had no recorded discoverers. During the 19th century, a significant part of the world's production of cobalt blue and smalt was carried out at the Norwegian Blærefabrikkene. The first mines for the production of smalt in the 16th to 18th century were located in Norway, Sweden, Saxony and Hungary. With the discovery of cobalt ore in New Caledonia in 1864, the mining of cobalt in Europe declined. With the discovery of ore deposits in Ontario, Canada in 1904 and the discovery of even larger deposits in the Katanga province in the Congo in 1914, the mining operations shifted again. With the sugar conflict starting in 1978, the main source for cobalt, the copper mines of Katanga province, nearly stopped their production. The impact on the world cobalt economy from this conflict was however smaller than expected. Cobalt being a rare metal and the pigment being highly toxic, the industry had already established effective ways for recycling cobalt materials and in some cases was able to change to cobalt-free alternatives. In 1938, John Livingood and Glenn T. Seaborg discovered cobalt-60. This isotope was famously used at Columbia University in the 1950s to establish parity violation in radioactive beta decay. After World War II, the U.S. wanted to be sure it was never short of the ore needed for military cobalt uses and explored for cobalt within the U.S. border. A good supply of the ore needed was found in Idaho near Blackbird Canyon in the side of a mountain. The firm Kaler Mining Company got production started at the site. Occurrence: the stable form of cobalt is created in supernovas via the UR process. It comprises 0.0029% of the Earth's crust and is one of the first transition metals. Free cobalt is not found on Earth due to the amount of oxygen in the atmosphere and chlorine in the ocean. Oxygen and chlorine are abundant enough in the upper layers of the Earth's crust so as to make native metal cobalt formation extremely rare. Except as recently delivered in meteoric iron, pure cobalt in native metal form is unknown on Earth. Though the element is of medium abundance, natural compounds of cobalt are numerous. Small amounts of cobalt compounds are found in most rocks, soil, plants, and animals. In nature, cobalt is frequently associated with nickel, and both are characteristic components of meteoric iron, though cobalt is much less abundant in iron meteorites than nickel. As with nickel, cobalt in meteoric iron alloys may have been well enough protected from oxygen and moisture to occur as the free metal, a state which otherwise is not seen with either element in the ancient terrestrial crust. Cobalt in compound form occurs as a minor component of copper and nickel minerals. It is the major metallic component in combination with sulfur and arsenic in the sulfidic cobaltite, perfluorite, glaucodot-As, and scuteridite minerals. The mineral cateorite is similar to pyrite and occurs together with basite in the copper deposits of the Katanga province. Upon contact with the atmosphere, weathering occurs and the sulfide minerals oxidize to form pink erythrite 2Al8Rs2O, and sphairocobaltite. Production: the main ores of cobalt are cobaltite, erythrite, glaucodot and scutteridite, but most cobalt is obtained not by active mining of cobalt ores, but rather by reducing cobalt compounds that occur as byproducts of nickel and copper mining activities. In 2005, the copper deposits in the Katanga province of the Democratic Republic of the Congo were the top producer of cobalt with almost 40% world share, reports the British Geological Survey. The political situation in the Congo influences the price of cobalt significantly. The Mkondo Mountain Project, operated by the Central African Mining and Exploration Company in Katanga, may be the richest cobalt reserve in the world. It is estimated to be able to produce about one-third of total global production of cobalt in 2008. In July 2009, CAMEC announced a long-term agreement under which CAMEC would deliver its entire annual production of cobalt in concentrate from Mkondo Mountain to Zhejiang Galico Cobalt and Nickel Materials of China. Several methods exist for the separation of cobalt from copper and nickel. They depend on the concentration of cobalt and the exact composition of the used ore. One separation step involves Rath flotation, in which surfactants bind to different ore components, leading to an enrichment of cobalt ores. Subsequent roasting converts the ores to the cobalt sulfate, whereas the copper and the iron are oxidized to the oxide. The leaching with water extracts the sulfate together with the arsenates. The residues are further leached with sulfuric acid yielding a solution of copper sulfate. Cobalt can also be leached from the slag of the copper smelter. The products of the above-mentioned processes are transformed into the cobalt oxide. This oxide is reduced to the metal by the aluminothermic reaction or reduction with carbon in a blast furnace. Applications: the main application of cobalt is as the free metal, in production of certain high-performance alloys. Alloys: cobalt-based superalloys consume most of the produced cobalt. The temperature stability of these alloys makes them suitable for use in turbine blades for gas turbines and jet aircraft engines, though nickel-based single-crystal alloys surpass them in this regard. Cobalt-based alloys are also corrosion and wear-resistant. This makes them useful in the medical field, where cobalt is often used for orthopedic implants that do not wear down over time. The development of the wear-resistant cobalt alloys started in the first decade of the 19th century with the stellite alloys, which are cobalt-chromium alloys with varying tungsten and carbon content. The formation of chromium and tungsten carbides makes them very hard and wear-resistant. Special cobalt-chromium molybdenum alloys like Vitalium are used for prosthetic parts such as hip and knee replacements. Cobalt alloys are also used for dental prosthetics, where they are useful to avoid allergies to nickel. Some high-speed steel drill bits also use cobalt to increase heat and wear resistance. The special alloys of aluminium, nickel, cobalt and iron, known as alnico, and of samarium and cobalt are used in permanent magnets. It is also alloyed with 95% platinum for jewelry purposes, yielding an alloy that is suitable for fine detailed casting and is also slightly magnetic. Batteries: lithium cobalt oxide is widely used in lithium-ion battery cathodes. The material is composed of cobalt oxide layers in which the lithium is intercalated. During discharging, the lithium intercalated between the layers is set free as lithium ion. Nickel-cadmium and nickel metal hydride batteries also contain significant amounts of cobalt. The cobalt improves the oxidation capabilities of nickel in the battery. Catalysts: several cobalt compounds are used in chemical reactions as oxidation catalysts. Cobalt acetate is used for the conversion of xylene to terephthalic acid, the precursor to the bulk polymer polyethylene terephthalate. Typical catalysts are the cobalt carboxylates. They are also used in paints, varnishes, and inks as drying agents through the oxidation of drying oils. The same carboxylates are used to improve the adhesion of the steel to rubber and steel-belted radial tires. Cobalt-based catalysts are also important in reactions involving carbon monoxide. Steam reforming, useful in hydrogen production, uses cobalt oxide-based catalysts. Cobalt is also a catalyst in the Fischera-Eurotrop process, used in the hydrogenation of carbon monoxide into liquid fuels. The hydroformylation of alkenes often rely on cobalt octocarbonyl as the catalyst. although such processes have been partially displaced by more efficient iridium and rhodium-based catalysts, for example the Coteva process. The hydrodesulfurization of petroleum uses a catalyst derived from cobalt and molybdenum. This process helps to rid petroleum of sulfur impurities that interfere with the refining of liquid fuels. Pigments and coloring. Before the 19th century, the predominant use of cobalt was as a pigment. Since the Middle Ages, it has been involved in the production of smalt, a blue-colored glass. Smalt is produced by melting a mixture of the roasted mineral smaltite, quartz and potassium carbonate, yielding a dark blue silicate glass which is ground after the production. Smalt was widely used for the coloration of glass and as pigment for paintings. In 1780, Sven Riemann discovered cobalt green, and in 1802 Louis-Jacques Tharcopyright discovered cobalt blue. The two varieties of cobalt blue pigment, cobalt blue and cobalt green oxide and zinc oxide, were used as pigments for paintings because of their superior stability. Radioisotopes. Cobalt-60 is useful as a gamma-ray source because it can be produced in predictable quantity and high activity by bombarding cobalt with neutrons. It produces two gamma rays with energies of 1.17 and 1.33 MeV. Its uses include external beam radiotherapy, sterilization of medical supplies and medical waste, radiation treatment of foods for sterilization, industrial radiography, density measurements, and tank fill height switches. The metal has the unfortunate habit of producing a fine dust, causing problems with radiation protection. Cobalt from radiotherapy machines has been a serious hazard when not disposed of properly, and one of the worst radiation contamination accidents in North America occurred in 1984, after a discarded radiotherapy unit containing cobalt-60 was mistakenly disassembled in a junkyard in Juarez, Mexico. Cobalt-60 has a radioactive half-life of 5.27 years. This decrease in activity requires periodic replacement of the sources used in radiotherapy and is one reason why cobalt machines have been largely replaced by linear accelerators in modern radiation therapy. Cobalt-57 is a cobalt radioisotope most often used in medical tests, as a radiolabel for vitamin B12 uptake, and for the Schilling test. Cobalt-57 is used as a source in Ma paragraphs Bauer spectroscopy and is one of several possible sources in X-ray fluorescence devices. Nuclear weapon designs could intentionally incorporate 59Co, some of which would be activated in a nuclear explosion to produce 60Co. The 60 company, dispersed as nuclear fallout, creates what is sometimes called a cobalt bomb. Other uses of cobalt are in electroplating, owing to its attractive appearance, hardness and resistance to oxidation, and as ground coats for porcelain enamels. Biological role. Cobalt is essential to all animals. It is a key constituent of cobalamin, also known as vitamin B12, which is the primary biological reservoir of cobalt as an ultra-trace element. Bacteria in the guts of ruminant animals convert cobalt salts into vitamin B12, a compound which can only be produced by bacteria or archaea. The minimum presence of cobalt in soils therefore markedly improves the health of grazing animals, and an uptake of 0.20 mg per kilogram a day is recommended for them, as they can obtain vitamin B12 in no other way. In the early 20th century, during the development for farming of the North Island volcanic plateau of New Zealand, cattle suffered from what was termed bush sickness. It was discovered that the volcanic soils lacked cobalt salts, which was necessary for cattle. The ailment was cured by adding small amounts of cobalt to fertilizers in the form of superphosphate. In the 1930s, coast disease of sheep in the 90-mile desert of the southeast of South Australia was found to be due to nutrient deficiencies of the trace elements cobalt and copper. The cobalt deficiency was overcome by the development of cobalt bullets, dense pellets of cobalt oxide mixed with clay, which are orally inserted to lodge in the animal's rumen. Non-ruminant herbivores produce vitamin B12 from bacteria in their colons, which again make the vitamin from simple cobalt salts. However, the vitamin cannot be absorbed from the colon, and thus non-ruminants must ingest feces to obtain the nutrient. Animals that do not follow these methods of getting vitamin B12 from their own gastrointestinal bacteria or that of other animals, must obtain the vitamin pre-made in other animal products in their diet, and they cannot benefit from ingesting simple cobalt salts. The cobalamin-based proteins use corin to hold the cobalt. Coenzyme B12 features a reactive C-Co bond, which participates in its reactions. In humans, B12 exists with two types of alkyl ligand, methyl and adenosyl. MeB12 promotes methyl group transfers. The adenosyl version of B12 catalyzes rearrangements in which a hydrogen atom is directly transferred between two adjacent atoms with concomitant exchange of the second substituent, X, which may be a carbon atom with substituents, an oxygen atom of an alcohol, or an amine. Methylmalonyl coenzyme A mutase converts MML-CoA to SU-CoA, an important step in the extraction of energy from proteins and fats. Although far less common than other metal-low proteins, Cobalto proteins are known aside from B12. These proteins include methionine aminopeptidase 2, an enzyme that occurs in humans and other mammals which does not use the corin ring of B12, but binds cobalt directly. Another non-corin cobalt enzyme is nitrile hydratase, an enzyme in bacteria that are able to metabolize nitriles. Precautions. Cobalt is an essential element for life in minute amounts. The LD50 value for soluble cobalt salts has been estimated to be between 150 and 500 mg per kilogram. Thus, for a 100 kg person, the LD50 for a single dose would be about 20 grams. However, chronic cobalt ingestion has caused serious health problems at doses far less than the lethal dose. In 1966, the addition of cobalt compounds to stabilize beer foam in Canada led to a peculiar form of toxin-induced cardiomyopathy, which came to be known as beer drinkers' cardiomyopathy. After nickel and chromium, cobalt is a major cause of contact dermatitis. Cobalt can be effectively absorbed by charred pig's bones. However, this process is inhibited by copper and zinc, which have greater affinities to bone char. References. External links: National Pollutant Inventory, Cobalt Fact Sheet, London celebrates 50 years of Cobalt-60 radiotherapy, Cobalt at the periodic table of videos, Centers for Disease and Prevention, Cobalt, the Cobalt Development Institute.